In this section, we will discuss higher order electromechanical effects, electrostriction, which is the effect which relates square of the field with the strain. Before we do that, I would like to make a comment on something that we did at the very beginning of the course, where I defined the piezoelectric effect and ask you to think about this situation where we apply pressure on the sample. We have charges, and I will mark this side with A and this side with B. And I asked you what would happen if you turn the sample by 180 degrees. Now have in mind that the pressure here and here must be exactly the same. It's tangential pressure, sample doesn't move. The pressure that is acting on the sample is same on both sides. So if you turn sample upside down, and we have to start with this situation, then the only thing that can happen when we turn the sample upside down is that we have here again negative, and here we have positive charges. What this actually tells us is that this sample was to start with asymmetrical. The side A and side B are not equivalent. And we call those materials, there is more rigorous definition, and we will come to that later, but these are non-centrosymmetric materials, and they are piezoelectric, most of them. There are some exceptions. There are some exceptions, as you will see later. If material is centrosymmetric, then in this situation where we apply pressure, there can be no charge on side A, and B, there can be no charge. And if we rotate the sample, the same thing, there is no charge. Okay. So these are centrosymmetric materials, and they are not piezoelectric. Now, as you will see, one always has to take these things with a caution. I will show you how, by using electrostrictive effect, you can in fact make non-centrosymmetric materials piezoelectric. Of course, there is a trick, but there is a way to change their symmetry without really affecting material itself. So we'll come to that. We'll come to that next. So what is electrostriction? We will consider material which is centrosymmetric. So we will take centrosymmetric material. You see that it is centrosymmetric because with respect to this central atom, all other atoms are placed, distributed symmetrically. This material cannot give us piezoelectric effect. However, it can still change its size by applying electric field. Why? Well, because if these are positive and negative charges, when we apply electric field, positive charges will move in one direction, negative charges will move in the other in another direction, and that means that we will have here some net change in dimension and some strain x, which is equal delta L cross L. So here I'm using symbol x for strain. Now, if we turn electric field by 180 degrees, you remember what happened in piezoelectricity. If we change the direction of the field, the sample will shrink. If sample would do opposite of what it was doing with the field in the opposite direction, so sample can shrink and extend. And here, sample in this particular case will extend in for both positive and negative fields. So if we take this as a reference value, you see that it has again extended. The length of the sample is L plus delta L, and here it's delta L plus, L plus delta L. This is the principle of electrostriction effect. The simple drawing is actually too simple, and if you dig in a little bit deeper, the drawing would, illustration of electrostriction with this drawing would in fact fail, but we will use it to illustrate the principle. Mathematically, electrostriction is described by this formula here. Electrostriction is the tensor of the fourth rank, which means that it is present in all materials, centrosymmetric and non-centrosymmetric alike. You can apply fields in same direction or different directions. If it is, if there is only one direction of the field, we have here E square, and but we can also apply field in different directions, and M is so-called electrostrictive coefficients. So the bottom line is that for both directions of the external stimulus, the object deforms by the same amount. To properly describe electrostriction, one would have to make some kind of bonds between different atoms, and those bonds should be anharmonic. But I don't want to go into that. If you are interested, you can consult books by Uccino that I gave you at the beginning, where he goes with some phenomenological description of electrostrictive effect. So to summarize, when we look, for example, at a strain can be obtained in a material by applying a pressure, Hooke's law, by applying electric field, piezoelectric effect, and this of course is possible only if material is non-centrosymmetric. So this term is always present. This one is not if material is centrosymmetric. And finally, we have a piezoelectric electrostrictive effect, which is present in all materials. And then we can continue here with yet higher order terms with E cubed and so on. As similar to piezoelectricity, which we could represent in terms of electric field or polarization, strain or stress, we can also present electrostriction in terms of polarization. And in that case, we would have a relationship which is X equal to Q P square, and relationship between Q and M coefficients is giving by this relationship here. I will come to that later on. So important to remember, electrostriction effect is present in all materials regardless of symmetry. It is in general much smaller than piezoelectric effect, an order of magnitude or more. And you should remember that piezoelectric strain is ideally linear with electric field, while electrostrictive strain is parabolic with electric field. And that is how you can distinguish between them. When you measure your strain, if you get that it changes as a square of the field, then you have to see whether you have electrostriction, or maybe, as you will see later on, you actually have piezoelectric effect, but other contributions which can make it which can make it field dependent. Now, I would like to illustrate to you how these nonlinear effects look like in a general case, not only for electrostriction. So we will use this drawing here. We will imagine that our coordinate system is given here. So this is plus motion. So this orange atom here can move along horizontal axis, and it can move along vertical axis. Now, to make this more readable, I will erase this coordinate system, but please remember that that this is positive, and this is positive, and this is negative motion. So I will now clear the page. So imagine that we apply a force which is sinusoidal with time, and that response is square of the force. We obtain this, and we can easily find out that sin square omega t can be expressed with this formula. Note that for a response, we have twice the frequency of the stimulus. Now, if you apply force up, down, and then change direction of the force, this plus atom will move left and right, but will also move in the vertical direction toward this negative atom. So the movement of the orange atom will go like this. It will have horizontal and it will have vertical component. Vertical component we will describe by green lines, and with the red lines we will describe horizontal movement. So let's apply force at 0 and go to maximum. So here. So the orange atom will move like this, and it will also move like that. So it will make this motion, and it will make this motion. Then we go from maximum down back to 0. Okay. The orange atom will go down from here to here, while the green will go from top to bottom. So force goes like this, horizontal movement goes like this, and movement of the green atom is like that. Now we change direction of the force. Force goes down. Positive atom will move in that direction, negative direction. While in a vertical direction, it will again move vertically. So when force goes down, horizontal motion is like this, while the vertical motion is again in the positive direction. Vertically, it always moves in a positive direction. Horizontally, it moves either in a negative or positive direction. Once we are here at a maximum, negative maximum for the force, we now go back. So being always in a negative direction, it goes back to 0. So from this point to here, while in vertical direction, it goes from this maximum point back to the 0. It goes from here to here. So while the force makes one period and horizontal displacement makes one period, the green line does this. So the frequency is 2 times frequency of what you have there. So that's what's happening with the so-called second harmonic in nonlinear motion. And that's what electrostriction would do. Piezoelectric effect would go up, down, then change direction, go maximum negative, go back to 0, while electrostrictive will always go either only positive or only negative, depending on whether this coefficient m is positive or negative. There are 2 definitions of electrostrictive effect, just like what we did with piezoelectricity, depending on boundary conditions. So we can express strain in terms of electric field or polarization, and of course the proportionality constant must be different, since P, polarization, is equal to field multiplied by the electric susceptibility, and this susceptibility is very close to permittivity or kappa. We can get information on how Q and M are related. So let's look here. Q times E square. So Q square E square. So this is he. Okay, so that means that M is equal to Q. And what that means is that if we plot here, for example, polarization and electrostrictive strain as a function of field, we see that in most materials, polarization is nonlinear, and that strain is not parabolic. It's parabolic at low fields, but at high fields, where polarization is no longer linear, it starts bending. If you do it as a function of P or P square here, you will get a straight line. What this basically means is that this equation is more fundamental than this one. Here, you have permittivity or susceptibility. Susceptibility and permittivity are very close to each other in high permittivity materials such as ferroelectrics that we will discuss, but not so in low permittivity materials. And since we have here influence of the permittivity, which is a function of temperature of field, remember permittivity is delta P over delta E. So kappa or permittivity is derivative of polarization with electric field. So as polarization changes with the field, so that means that the permittivity has to change with the field, and therefore electrostrictive strain is not parabol but starts deviating from it. While for a Q coefficient, the slope here is a Q coefficient, we have almost straight lines. Actually, it starts bending a little bit. There are some other contributions to this electrostrictive coefficient. Now, what's interesting, while electrostrictive effect is by itself used in some applications, which we will discuss later on, it is interesting that we can use electrostriction to build, to engineer piezoelectric response in a centrosymmetric material. How can we do that? Well, we start with this relationship and then assume that our field is a combination of an AC field and a DC field. That means that if we plot field here and this is time, that our field looks something like this. There is a DC component, a static component, and AC component, which varies with time. And we take that this AC component is relatively small. We calculate this, we get this. This is just a constant term. M is constant. Electric field DC squared is constant. This is pure electrostrictive effect, which we will neglect simply because it is small. It's still there, but we will neglect it because it's small. And we get that strain is equal to this term here times AC field. Now, this is nothing else but expression for piezoelectricity. This is a constant times AC field, strain, which is a function of AC field in a linear fashion. That's nothing else but piezoelectric constant. So the equivalent piezoelectric constant here is equal to 2ME DC. We can do the same with the polarization, and we get that this induced piezoelectric coefficient is equal to the product of permittivity, Q coefficient, and induced polarization. How is this possible? Well, once you apply electric field, DC electric field, on a centrosymmetric material, that electric field will induce polarization in the material and will therefore make it non-centrosymmetric. If you have a vector polarization, it's not centrosymmetric because this part is different than this part. Now, the nice trick is that you actually don't have to apply external electric field to make material piezoelectric, to make centrosymmetric material centrosymmetric. There are tricks how this can be done without actually physically applying electric field. You can find a discussion of that in this paper here, but basically what you do, let's assume that we have a centrosymmetric material, okay? And then on the top of that material, we have electrodes. And let's say that we make these electrodes different. So this is metal, and this is our insulator or semiconductor, semiconducting centrosymmetric material. Now, whenever you have a junction between metal and insulator or semiconductor, you will bend conduction band. You will deplete material a little bit with for example, electrons. You may have some concentration of defects at that junction, and in general you will have that this electrode, this side of the sample and this side of the sample have different charges concentrated on them because these two metals are different, and that will produce a field in the sample. That field is enough through piezoelectric that field is enough to break the symmetry of the material, and then if you apply either AC electric field or pressure, you will actually get piezoelectric like response. And in this paper here, This was done simply by taking a semiconducting material, applying pressure on it, and then putting two electrodes, which are different, in this case, aluminium and gold. They bend bends in the material in a different way. There will be a field in that region of the material, and material will behave like it is piezoelectric. The effect is actually relatively small, but it's interesting. This has been observed years before, especially in thin films. So what you would get in thin films is the following. Whenever you have a film, okay, so let's say this is film, then usually on the bottom of the film you have to have some layer to prevent film reacting with the substrate, and then you have your substrate, and somewhere here you will also have an electrode, okay? And on the top of the film, you will have another electrode. So basically what you are going to have is that the bottom and the top of the thin film are different. You have a metal here, those are two different electrodes which you use to make a contact of your thin film with the world, to apply field on it, to collect charge, current, and so on. And the effect would be exactly the same as described in this paper. So this has been observed years ago and reported in the literature. Thin films are almost never perfectly symmetrical, and due to this, you can produce effects, different effects, and one of them is to induce piezoelectricity in materials that are normally not expected to show any piezoelectricity.